Hi students, hope you guys are doing good. Today is the second lecture corresponding to geared mechanisms. Last time we discussed single gears, the nomenclature, the terminologies, the diction associated with such gears, how to manufacture them, what is the pressure angle, what is the line of action, and quite a few other terminologies. And we are able to understand how gears are manufactured and what are the different types that are available. Today is going to be appropriate that we connect these single gears together. And this is what we're going to call gear trains. There can be multiple ways in which we can join them together. We are going to discuss those. And there are quite a few applications that are governed by gear trains. We're going to briefly discuss those as well. So let's start today's lecture. It would be appropriate before we start our discussion to revise the fundamental law of gearing. It says that the angular velocity ratio between the two meshing gears is going to remain constant. Angular velocity ratio would mean that you're discussing omega out over omega in, where omega out is the angular velocity of the output gear divided by the angular velocity of the input gear. So this is going to remain constant. But this constant is going to be dependent on geometrical features, and that was what we discussed last time with these expressions in mind. We said that the angular velocity ratio mv is going to be equal to omega out over omega in, but this is going to be equal to r in over r out, which is the ratios of the radii of the meshing gears, which is obviously going to be equal to the ratios of the diameters as well. But today we're going to add a little additional feature, because we have discussed the gear tooth profile in much more detail last time, so it would be kind of appropriate now to add that little expression over here. And that is going to be equal to n in over n out, which means the number of teeth of the input gear divided by the number of teeth of the output gear. So this is going to indicate that we can count the number of teeth, and that is going to give us the angular velocity ratio, which is going to remain constant in two meshing gears. So this is going to be a very nice expression to use whenever there is a multiple set of gears meshed together, or a gear train, if I may say that. And the relationship between the mv and mt is just like these are inverts of each other. So this is like inversion. So with this realization that you are going to make use of fundamental law of gearing, we are going to again and again reiterate these expressions in this subsequent discussion. Generally, there are three types of gear trains: simple, compound, and planetary. And if we go from simple all the way to planetary from top to down, we are adding complexity in the systems. So this added complexity is not without reasons. There are going to be certain rationale or reasons behind adding this complexity, and those being the gear ratios. If we wish to have higher gear ratios, how to handle that? Space, for example, backlash, service life, etc. So there are going to be certain reasons which are going to add this complexity in the systems, asking us to shift from simple to compound, and from compound to planetary types of gear trains. The very first type of gear train that we are going to discuss is called simple gear train. The term simple suggests that you are going to simply add the gears together, and because of the simple construction of such gear trains, we have used this word. How to construct those? Let's have this demonstration now. So just observe in the diagram over here, you have the angular velocity provided into the mechanism at gear number 2. Gear number 2 is going to have a rotation, forcing the gear number 3 to have the output. The ratios between the angular velocity of the two is going to be N2 over N3, where N2 is the input side, and this is the number of teeth, and N3 in this case is going to be the output side, and obviously this N is indicating number of teeth as well. So if I just say that I'm going to get the output at gear number 3 using this expression, this would be right. But obviously this is needed to be further augmented, and that is when we add another gear in the mix. So if we add this gear number 4 into the system, this is going to add a bit of complexity, and that is just like in the expression you have added N3 over N4 to the previous expression, which is obviously in a similar scenario, the number of teeth on the input gear, which is now gear number 3, over the number of teeth on the output gear, which is now N4. If I keep on doing this for N5, you are going to add another expression, and similarly for N6, another ratio is going to be added in the expression. So now if you observe the diagram, you can see omega n provided to the gear number 2 right over here, and omega out produced as the output. And that is going to be just like we have gradually added these gears in the gear train. And now back to the expression. If you just observe how the expression has panned out, you can see that N3 in the denominator over here can be cancelled with N3 in the numerator over here. N4 can be cancelled with N4. N5 similarly can be cancelled with N5. And you are going to be left with a very simple expression right over here, which is omega out over omega in is equal to, I'm going to rewrite that over here, N2 over N6. And what was the number of teeth in between for these gears? That is immaterial in this expression. Now with this realization that you have constructed a simple gear train by simply adding the gears in the train, that's why we call this as to be a simple gear train. And obviously you can see that there are certain features associated with it, and these are listed right over here, and the most useful is listed right over here, which says that it is useful for changing the direction and obviously covering the distance from this point all the way to this point. So it has covered a distance, means that you can have the input provided a bit distance apart from where the output is required, and also you can change the directions if needed. So the number of gears added in the mix is going to have the reversal in the direction whenever you have the meshing gears. And obviously because you can see that the gears have been added, but you can get a gear ratio, but you cannot really get a big gear ratio in this scenario because of the practical reasons that the space this mechanism is going to require is going to grow bigger as the gear ratio is going to be required. Higher gear ratios are required, and similarly for the practical reasons, you wish not to have those many mechanical components added just to cover distance. You can use the belt drives if needed be. The synchronous belts were discussed last time. We can possibly use those. So from practical reasons and also because some alternates are available, simple gear trains are not always the best option. And the limiting factor we have already discussed, that the gear ratio is indicated to be on the lower side. So with this realization that it has got certain limitations, we are going to move forward. In this continuation, we may raise this question that what if we require larger gear ratios, maybe 20, maybe 100? Is there any suitable option available? Or alternatively, what if we wish not only to conserve this space but to transfer the torques in much more effective manner? And similarly, some other questions may be raised, so I'm going to try to uh, answer these queries in the subsequent slides. Compound gear trains can potentially offer answers to these queries. The term compound means that you are going to assemble these gears in a bit complex manner. How that process takes shape, let's pictorially observe the process. To start with, we are going to have one input shaft. This input shaft is going to have a rotation about a specific axis in either clockwise or counterclockwise direction. And this axis is going to be defined with the center line over here. The long dash line as indicated right over here. The gear is going to be mounted on this shaft as is indicated with number of teeth N2 over here. So this is the input side, and the type of gear that we have got is helical gear. So this provides the input. The other thing that you can observe is that the shaft is supported on both the sides with the bearings. So these bearings are important machine elements which are going to house the gear trains and support the shafts to have nice rotation going on. So the next step would be to add something to the single gear in order to make it a gear train. And that we have added in this manner. Now you can see obviously that the other gear that we have added, let it be like indicated with N3, is also going to have a shaft whose center line is indicated over here. But on this shaft, you're going to have this gear mounted, and you can observe right over here that the number of teeth for this is going to be different from the number of teeth on the input gear. And that is going to change the speed and the torque associated with this mechanism. Now, the next step would be how to add the other gears with this gear train in order to make it compound gear train. And that is interestingly done in this manner, that on this shaft that I've just indicated, on which N3 is mounted, you have another gear, concentric, on the same shaft mounted, with N4 as the number of teeth for that gear. Now, if you have on a single shaft two gears mounted, that's going to make it a compound gear train. Now, obviously N4 may not be the output gear. You may need to add another gear with this N4, potentially going to give you output shaft. So that is indicated with N5 as the number of teeth for the output gear, and the shaft which is going to have a rotation after you have passed on intermediate stages, that is indicated with this center line over here. Now with this realization that you have got the gears assembled together, not in series, but somewhat kind of involving a bit of complexity, that's why we call these kinds of gear trains to be the compound gear trains. Now I can also make you see the other view as well. if you view it from the front, this would look potentially like this. And you can obviously see the input side over here, the output side over here, and in between you have the intermediate stage. But this intermediate stage should always remain in your mind that it is like two gears mounted on the same shaft, making this gear train to be the compound gear train. Now, obviously, these are the features associated with it. You are going to have more than one gears mounted on a shaft, and it allows for larger gear train ratios. And that's the benefit. That was the question that we raised in the previous slide, and that's exactly the answer this compound gear train offers as a unique way of assembling these gears together. Now, the other question would be that what is going to be the driving expression? The driving expression is going to be this. And let's kind of quickly follow that. So the stage, let me use a different color over here. The very first stage, if I use green color, is encapsulated over here. And this is going to have the reversal in direction. So that's going to be indicated with a negative sign, because whenever you have two gears connected in series like this, we have seen that previously that the direction is going to be changed. So this is going to be N2, which is the input side, number of teeth on the input gear, divided by N3. And if I use another color, let it be like blue for the second stage over here, this would indicate similarly the direction reversal minus, and that is going to be on the input side N4 and on the output side N5. So since you have mounted these two gears N3 and N4 on the same shaft, you can just multiply these two ratios together as indicated in this expression. And that is what is indicated right over here. You have minus N2 over N3, similar to this, and you have minus N4 over N5 from here, multiplied together. So this is going to be the governing expression for the compound gear trains. At this stage, it would be important for us to understand the design process as well. The designing of compound gear trains would require answers to a few questions, and these questions can be that how many number of stages we would require, how many number of teeths we may require to have on the individual gears, what is going to be the resultant gear ratio. That is going to be another important design aspect. And potentially, if we can make the manufacturing or assembly easy, slash manufacturing. So if we can answer these questions, that would be great in this design process. So let's observe what is happening over here in this diagram. You can see that the input is provided over here on this side in terms of angular velocity provided to the shaft. The gear labeled as gear number 2 is going to have a rotation. This rotation is going to be transferred to gear number 3. And this gear number 3 is going to force gear number 4 to have a movement. And obviously you can see that the shaft is connecting the two gears together. So whatever is the angular rotation happening for gear number 3, the same is going to be exhibited by 4. And then 4 is forcing gear number 5 to have a movement and produce the shaft rotation in terms of angular velocity on the output side. So this is the output. So you can see the process. And in this case, you can see that the stages are 2. And obviously these are pictorially represented as well. Now the expression we have seen in the previous slide is once again written down over here. The only change that you can observe is that the negative sign over here and the negative sign over here, because of the multiplication of the two, has been taken out from the expression. The rest is same. Now at this particular stage, I can say that if I choose the number of teeth appropriately, N2, N4, N3, and N5, I can achieve any demanded gear ratio. And if two stages are insufficient to provide me that gear ratio, I can obviously add another stage and try to achieve that gear ratio. The other thing that I can observe from this expression is that uh, although these two are N2 and N3 in this case, and N4 and N5 are the number of teeth uh, of the uh, involved gears, I can readily observe that I can have a design decision made by saying that if N2 can be selected to be equal to N4, that is going to potentially make our life a bit easy. And that would mean, in other words, that this gear selected over here is going to have the same number of teeth as gear number 4. And similarly, for N3 to be equal to N5, I'm going to ask this gear to have the same number of teeth as this gear number 5 over here. And this is going to potentially uh, make our life very easy. And that is because rather than designing 4 different gears, I would only design or manufacture 2 types of gears. And because the gear number of teeth are going to be same uh, in pairs, you are going to add them in much more easier fashion. So that is when you do that, eventually the expression is going to be this, which over here the power is indicating the number of stages, and the number of teeth of the involved gears are indicated in this ratio as well. So with this realization that the compound gear train is going to be designed corresponding to the expression that we have listed, it is a very easy expression to interpret, and you can do quite a lot of stuff in order to try to answer these queries that we have raised: number of stages, number of teeth, gear ratio required, ease of assembly and manufacturing in these cases. So let's do one exercise. We're required to design a train with a gear ratio of 180 to 1. And obviously you can make comparison with the simple gear trains. This number was not possible over there. So if you have that requirement, the very first thing that you can attempt is to consider that you have a 2-stage compound gear train. And if you have a 2-stage compound gear train, it would be something like you take the square root of 180. And this turns out to be 13.4164, which is a big number, by the way. And it would mean that if you provide 1 as the input, the output is going to be 13 times higher. It depends on the ratios to discuss the speed or the torque alternatively. But 13 is a big number. 13.4 is a big number. We can all agree to that. So it would mean that the 2-stage arrangement is not going to be that possible. So let's move on and assume that you can have 3 stages. So if you have 3 stages, you can take the cube root, and this turns out to be 5.64. And now this is something achievable. And this would mean that I can assume this as the intermediate gear ratio between the stages. And since you have 3 stages, you can have eventually achieved 180 to 1 ratio. Now the other stage is going to be how you're going to define the pinion teeth. And we have in the last lecture discussed that if you have too few pinion teeth, it is going to be a bit difficult for the pinion to have a rotation. So you need to consider quite a few standards over there, and quite a few considerations. So in this particular case, if I choose ranging from 12 all the way to 16, you can see a few options laid down, keeping the intermediate ratio like 5.646. Then in the next gear in the stage is going to have 67.75 as the gears over here. Similarly over here, if you choose 13, if you choose 14, this is going to be the answer, and so on and so forth. So in order to keep this ratio like in the second column intact, you need to have the gear teeth of the mating gear or the meshing gear to be decided in this fashion as indicated in the third column. Now with this realization that we have to choose something, we are going to choose 14 pinion teeths, and with that this turns out to be 79.04 teeths on the next gear. So with this realization that if you choose for that kind of arrangement, we take the ratio 79 to 14, 79 coming in from this side and 14 coming in from the pinion side. The power is indicated because it is the 3 stages, and this turns out to be 179.67 as the gear ratio. And obviously you can see that this is not actually 180, this is just below that. So if you are only considered, if you have only considered the force or the torque transmission, then it would be something like appropriate or possibly suitable. But if the timing is concerned, if the timing is required as well, then it is not going to be that suitable. If you need to have a precise timing on the gears, obviously you would not allow a discrepancy over here. You would require 180 to be achieved exactly. So that's why in this particular arrangement we have identified a bit of flaw that we need to rectify. We will do that, but in the next slide. Let's do this exercise, but now try to achieve the exact gear ratios. So the given is like you have the gear ratio of 180 to 1, that is given. The other thing that we know or we have selected up to this point is like you have the pinion, which is going to be having 14 teeth on it. So with this realization that we have got this as the input data and then we have to design a compound gear train, let's start the discussion. So the solution is going to be something like this. The very first stage, I'll try to factorize the gear ratio. So if I just take 180 as the number, it would mean that you can have something like 2 into 90, something like that, or 2 into 45 alternatively, or you can further do factorization of 45. There's going to be 2 into 2 into 3 into 15, something like that, and that you can do something like 2 into 2 into 3 into 3 into 5, something like that. And then you can make some combinations as well. For example, this can also be, if I just take like this 4 into 3 into 3, 9 into 5, something like that. Or alternatively, I can pair this 2 with this 3 over here, and similarly others. So this is also going to be possible, like you have 6 into 6 into 5, something like that. And now when you have all the factors in front of you, you are going to kind of have a look on it and see what is the physical sense of it. So the very first one, for example, over here would mean that you have something like 2 stages where you have 90 as the ratio achieved, which is obviously unrealistic. And similarly, you can have smaller pairs over here, and you have a big gear ratio over here. This is also going to be something like unrealistic. These can be realistic, but you can obviously see that now you, rather than having 2 or 3 stages, this is like 4 stages, which is going to be overly complex, if I may say that. So that's why we have done this exercise, to combine uh, some factors in a fashion that they give you lesser number of stages. So over here, in this kind of arrangement, you have 3 stages, and from here I can see that, yeah, that would be appropriate, but whether 4 into 9 into 5 would be a good option to have, or 6 into 6 into 5 is going to be a good option. And obviously I can see that 6 into 6 makes sense, because you're going to have 2 similar stages, rather same stages. And there is going to be the third one, which is a bit different. So if you have similar stages, as we have previously mentioned, that you can opt for the same types of gears selected, and that is going to make your assembly or integration job a bit easier. So I'm going to choose this one for the same reason. And that would mean that you can have answer to the second question, that is number of stages, by observing these factors. Now, once you have the number of stages indicated, you can jump onto the third step, and that is going to be something like defining the configuration of stage number 1. So stage 1 is going to be indicated. So this is going to be something like you have the very first number taken out from this combination, 6 into 6 into 5. So 6 into pinion gears, a number of teeth on the pinion gear, like 14 teeth, that is going to be 84 teeth on the first gear. So this is going to be, if I may say that, N3, because opinion is defined to be as N2. Now this is a very good result, by the way, because you can see that it is just going to make use of the input side from the pinion to be used with the stages that you have taken out from the factorization exercise. You can go to the stage 2. Stage 2 is going to have, for the second gear, something like, once again, the second letter coming in from here, 6 into 14 once again, which is the second gear in the compound gear. I'll draw that as well in order to make you see that. That is going to be equal to, once again, 80/40. Now, at this particular stage, it would be appropriate to visualize the whole process before we move forward. So that would be something like, you have on the input side a pinion, and this pinion is going to be having 14 teeth. So this is N2, indicated to be N2. And this is getting engaged with the first stage that we have just mentioned, something like that, where N3 is indicated to be having 84 teeth over here. This would be a bit bigger, so I can do something like that. Just to be consistent. And that is going to have a shaft over here. On the other side of this shaft, I'm going to have, once again, 14 teeth for N4. Now this is stage number 1. And why we have opted for 14 teeth, that's exactly the point that I've raised, that rather than designing the teeth to be different on all the gears, you would like to have pairs. So this gear over here is similar to this gear. All right, moving on. For stage number 2, you have once again 84 teeth to be structured. So I'm going to use blue again, and that would be something like another gear uh, getting engaged with the stage number 1. And that is also going to have 84 teeth over here. That's exactly what we have mentioned. And that is going to be equal to N5. So I'm going to write down over here to be N3, and this is going to be N5. So this is also going to have a shaft, and on the other side of the shaft, you are going to have once again 14 teeth, which is going to be equal to N6, if I may say that. And that is exactly the same type of gear that you have selected for N4 and N2. Now, once you have that arrangement, you can jump on to decide the stage number 3, which is the third stage. And that was having a gear ratio of 5 in it. So this is going to be 5 into 14. That is going to be equal to 70 teeth. And that's exactly what you're going to have at N7. So I'm going to use a different color, a green one, in order to indicate the last gear. And that is going to be N7, which is equal to having 70 teeth on it. And this is going to be producing the output rotation over here, which is in terms of omega out. So now you can see that it has got 3 stages in it. Stage number 1, 2, and 3. And that's pictorially shown right over here. The fourth step is going to be like checking whether you have done the whole stuff or the process correctly, and that is when you multiply these gear ratios together. So this is going to be something like you are going to check it, and that's when you say that 84 by 14 for the first, and then 84 by 14 for the second, and then use 70 by 14 for the third one is going to be equal to, and you can counter check that, that is going to be equal to 180. And that's exactly the gear ratio that we wanted to achieve. And by doing that, we have seen that in a stepwise fashion, starting from factorizing the gear ratio and then finding out, making some physical sense, and using the engineering sense that you have developed over the years to identify how many stages are going to be there, and then moving on to decide the intermediate stages over here, and then you have to check whether you have done the job correctly or not in order to achieve the exact gear ratio. So this is how you're going to design the compound gear train. And in this slide, I've kind of repeated the same exercise in a nicer format so that you can understand it in much more clear fashion. So 180 ratio 1 was needed to be factorized first. We did that. We can have multiple options, and then we wanted to keep the ratios to be same, about the same, and that exactly what we did. And the first stage, the second stage, the third stage was identified using the arrangement that we have figured out, and the total ratio was checked in the last stage to be this, thus exactly achieving the 180 ratio that we wanted to achieve. And this is going to ensure that you have that you're able to transfer the torques as well as execute the actions in a perfectly synchronized and timed fashion. This is what we have achieved through compound gear trains. Manual transmission in automobiles is a nice example of compound gear trains. In there, you would find quite a number of gears meshed together. And the primary objective is to transfer the engine power to the wheels. And when the low gear setting is selected inside the cabin, you would observe that the gear setting is going to be structured in a sense that it produces low speeds but high torques. And that is going to be something like starting from the input shaft connected with the counter shaft shown in yellow. And then the other gear on the counter shaft is going to be connected with the output shaft. And when you change the gear inside the cabin, it is going to change the position of the output shaft so that it is configured in a sense that low gear setting is selected. Now, in low gear setting, or in other words, when you try to start from the idle situation to the low speed setting, you would require the speed to be smaller, but the torques to be bigger, and this exactly achieves over here. And that is quite visible if you observe what is happening or what kind of arrangement is there between this gear and this gear. You can see the differences between the diameters of the two, and that is going to indicate what kind of output is going to be achieved. Moving on, when the speed of the automobile is grown higher, you can obviously reduce the torque, and that is what we call a high gear setting. In that, you can observe and you can kind of make comparison with the first diagram that obviously there is quite a bit of difference. Internally, this arrangement is selected in a sense that the output is now going to be generated from this gear rather than this gear. So the low gear setting has been disengaged and the high gear setting has been engaged, which means that you can now have higher speeds achieved, but lower torques would be there comparatively. If you wish to kind of reverse the direction of automobile, you can obviously do that, and that is an option available inside the cabin. And once you do that, you can see that there is this idler gear right over here that you can readily observe. This is the idler gear, which is engaged, and it is going to obviously, because of the engagement, reverse the direction of rotation. And that's exactly why the automobile starts moving backwards. So obviously you can observe over here that the manual transmission is obviously a very good selectable option of compound gear trains. And that's why it is being discussed over here. I can show you the arrangements over here. You can see the reverse direction animation going on. Because of the engagement of the idler, it reverses the direction. In case of higher gear setting now, you can see that the speed of output rotation is much higher and there is no idler engaged with it. And in case of low gear settings, you can see the output shaft is being rotated at much slower pace and there is no idle gear engaged in it. So you can see that animation again in order to gain much more insights into the manual transmission. One observation that we have not made in the previous diagrams is that the input shaft and the output shaft is when perfectly aligned, then it would be something like a reverted compound gears. And that example is being illustrated over here, but I'm going to indicate or do this exercise in much more detail in the next slide. Over here, you can see the reverted compound gear train. If I just start with the pictorial depiction of it, you can see over here the input shaft is being shown in the lower diagram. And the input shaft is structured in a sense that it provides the input from the user. And this is getting engaged over here with the counter shaft. Now, countershaft is structured in a sense that it has got, obviously, because of the compound gear train, two gears over here, N3 and N4. Now, on the other side, where you have N4 getting engaged around this interface to produce the output gear is structured in a sense that the input shaft, the center line of the input shaft is perfectly lined up with the output shaft over here. So you can see the center line over here is perfectly aligned in a sense that the output shaft is lined up with the input shaft. Now this is going to create another constraint. And this constraint equation is written down over here. This says that R2 plus R3, or the radii of gear number 2 and gear number 3, is when added, it is going to be equal to the radii of gear number 4 and gear number 5. Obviously, only then you're going to have the input shaft and the output shaft lined up. And that would mean, obviously, that you can say similar expression for the diameter, and you can say similar expression for the number of teeth on these gears as well. So this is going to be a constraint added in the design process in addition to the previous exercises. So all the remaining procedure is going to remain intact, and you just need to add this more constraint equation in the mix. So now the gear ratio is going to be structured in this expression. It says omega out over omega in is going to be equal to N2 over N3, which is one side, and N4 over N5, which is the second stage. If we wish to achieve a gear ratio of 18 to 1, we can do this exercise using the same expression. And that is going to be like you have the result of these two ratios multiplied together to be 18, because the gear ratio intended in this exercise is 18:1. So this is placed over here. And once you have that, you can similarly factorize, and you can say that, all right, I can opt for, let's say, one combination where you have 2 into 9 to produce 18, and then there is another alternate option like you have 3 into 6 to be equal to 18. So when you compare these two options, you would obviously see that over here you have some smaller gear ratio selected, and this one is a bit bigger than the earlier one, and these two are comparable. So that's why you would opt for this combination. So when you take that into account, you would say that N3 over N2 can be 6, and N5 over N4 is going to be equal to 3. And obviously, this is because of the factorization that you have previously mentioned or observed. So once done, you would say that that would mean that N3 is going to be equal to 6 times the N2 because of this expression, and N5 because of this expression is going to be equal to 3 times N4. With this realization, once done, you would say that the constraint equation was like N2 plus N3 to be equal to N4 plus N5. In other words, whatever is happening on this stage is going to be correlated with the stage in terms of number of teeth. So that's the constraint equation right over here. And as a result of that, when you plug in the N3 value over here from this expression and N5 from this expression, you would say that this is going to be your answer, which means 7N2 should be equal to 4N4, and that should be equal to a constant. And if C is taken to be 28, for example, then N2 would be 4 and N4 should be equal to 7, obviously because of this expression that we have just derived. Now, obviously, you can see that if you have a pinion which is going to have 4 number of teeth on it, it is going to be a too small number. And similarly, N4 over here is also a small number. So we have discussed it in the previous lecture that the power transmission and the pressure angles are going to be important aspects. So for that reason, we are not going to opt for N2 to be equal to 4. We need to have some bigger number. So we should take this C to be a bit bigger than that, and we can do something like that. 28 into 14 is selected over here. Let's like say that. You can opt for other numbers as well. And if you opt for that, N2 turns out to be 4 times this 4, which is going to be equal to 16, and N3 is going to be 4 times the previous number, which is going to be equal to 96, because it was previously indicated. 6 times the N2, 6 into 16 is going to be 96. And then similarly, N4 is going to be 28, which is going to be 7 into 4, and N5 is going to be equal to 3 times the N4, which is going to be 84. So these are the numbers that you have computed in order to achieve a gear ratio of 18 to 1 using the reverted compound gear train.